Hello, and welcome to our presentation on increasing electric vehicle adoption with multiple charger options. I'm Ron Stoll, the Power Product Marketing and Engineer at CUI. CUI is a power supply company specializing in AC to DC and DC to DC power solutions in the 1 to 500 watt range, such as those you may find inside electric vehicle supply equipment, powering the auxiliary circuits. And since 2020, CUI has been a Bell Fuse company and has been helping to expand their portfolio of power supplies and converters. Today, I'll be speaking to you about electric vehicle charging and the different types of chargers and EV supply equipment needed to support the transition from gas-powered vehicles to EVs. People drive for a variety of reasons. A single trip may be short or long, and there may be different lengths of time between trips, from the daily commute to cross-country road trips. Depending on the type of driving you're doing, it may be more or less important to charge the battery fast. You might think that we would always want to charge our batteries as fast as possible, but as we'll discuss, in many ways, or in many cases, it's unnecessary to charge fast, and there are benefits to using slower, less powerful chargers. This has led to multiple charging standards, specifying different charging methods and levels that can be used where most appropriate. We'll take a look at different chargers and charging levels and where it makes sense to apply them. The different charger levels and applications also lead to different requirements for the devices in the EV supply equipment, particularly the power supply. And so we'll look at some of the specific requirements to look out for when choosing a power supply for this equipment. And finally, the increase in number of EVs will also increase demand and stress on the grid. And so we'll take a look at how coordinated charging can improve power quality. But first, we'll take a quick look at some of the reasons behind the EV growth. Electric vehicles have been around for a long time, but until recently, their adoption was limited due to technological limitations compared to the internal combustion engine, and also because of cost. Two of the major technological roadblocks to the adoption of EVs have been their range and charge time. Electric vehicles are only now approaching the range of similar gas-powered vehicles, but it still takes longer to recharge the battery than to refuel a gas tank. Consumers often cite range anxiety, which is the fear of being stranded, as the reason for sticking with a gas-powered vehicle rather than adopting an EV. The thought of needing to wait several hours on a road trip to charge your battery isn't very appealing when a gas-powered vehicle takes just minutes. But the development of lithium-ion batteries, smaller, more efficient power electronics, and more public charging options have extended range and decreased charge time, making them more comparable to gas-powered vehicles. And, at the same time, climate change has made their adoption more critical, leading to both public and private initiatives to increase EV adoption. According to the EPA, in 2019, the transportation sector accounted for 29% of all greenhouse gas emissions, which made it the largest single contributor by sector. On top of that, the number of miles being driven is rapidly increasing. Prior to the pandemic, the US had seen a 48% increase in the number of miles driven by the average person over the last 30 years. Even with the recent increases in EV adoption, the EPA still estimates that 90% of energy for transportation comes from fossil fuels, and 50% of transportation emissions come from cars, trucks, and SUVs. These numbers make it clear that widespread EV adoption is a necessary step in the fight against climate change. Because of all of this, of electric vehicles becoming more practical in terms of battery capacity, charge speeds, and cost, and their importance in combating climate change, researchers are expecting EV adoption to increase rapidly over the next few decades. McKinsey estimates that in the next 10 years alone, the number of EVs and plug-in hybrid vehicles on the road will increase from 8 million to 120 million. The current White House administration is pushing to have electric vehicle sales make up half of all vehicle sales by 2030, while more conservative estimates put that date closer to 2050. To support this growth, many more chargers, both public and private, will be needed to be able to replace gas-powered vehicles in all situations. This graph also shows that plug-in hybrids will make up a good portion of the EV market in the near future, until the charging infrastructure can fully support an all-EV fleet and the range anxiety of consumers has gone away. To prepare for and encourage the increased adoption of electric vehicles, governments have been allocating funding and pushing plans for vast networks of charging stations. Recently in the US, the president laid out plans to increase the number of charging stations to 500,000 and allocate up to $7.5 billion to do so. In the UK, they're mandating that EV chargers be installed in new homes and that there will be no new petrol or diesel cars made after 2030. To help alleviate range anxiety and enable long range trips, the US is also creating alternative fuel corridors where EVs can travel and easily access charging stations along the way. The image on the right shows the map of existing and proposed corridors that will enable the driving of EVs almost anywhere across the country. And more public and private funding is going to finding new, faster, and more efficient ways to charge your vehicle, including embedding chargers into the road itself, which could allow for charging while you drive and even lead to reduced battery requirements in the vehicle. During the transition from internal combustion engines to EVs, the hybrid electric vehicle has been a way to reduce emissions without relying solely on batteries and not having the associated range anxiety to deal with. Hybrids combine most of the parts of both an internal combustion engine and an electric vehicle. There are several types of hybrid vehicles between mini, mild, and full hybrid, but in general, they all contain a gas engine, a battery pack, an electric motor, an inverter, and a generator that are placed in certain combinations of series and parallel to increase the efficiency of the ICE engine and even allow for short drives on pure battery power. Standard hybrids use their internal combustion engine to charge the battery with no option for external charging by more eco-friendly means. Plug-in hybrids, on the other hand, are basically an electric vehicle with a gas backup generator. They can drive on only battery power and use the gas engine to charge the batteries when the charge falls too low, but also have the option of using an external charger when possible to avoid using fossil fuels as much as possible. As you can see from the graph on the right, the combustion engine's torque profile peaks at high RPMs, but generates very little torque at slow speeds, whereas the electric motor has a flat torque profile and can provide peak torque at lower speeds. Hybrids use this relationship to operate their gas and electric motors at a more optimal and efficient point than they could achieve alone. In the series hybrid case, a gas engine is used to drive a generator which powers an electric motor that drives the vehicle. The gas generator is able to run at a more efficient operating point than if it were driving the vehicle by itself. In a parallel hybrid, both the electric motor and the gas engine may drive the vehicle either together or separately. Series hybrids tend to be more efficient for city driving with low speeds and lots of starting and stopping, while parallel hybrids are more efficient on highways where speed is high and relatively constant. Parallel drivetrains also tend to be more complex and expensive to implement. Now, within the range of hybrid vehicles are those that rely solely on the internal combustion engine to charge the battery, and those whose batteries may be charged externally, known as the plug-in hybrid vehicles. Plug-in hybrids may be configured in series or parallel, and this class of electric vehicle will need chargers. As the earlier McKinsey study showed, these plug-in hybrids are expected to make up a significant portion of the overall electric vehicle market for at least the next decade, and should be considered when looking at charger options. The standard hybrid vehicle can only travel 1 to 2 miles on pure battery power, after which the gas power is used to recharge the batteries and to power the vehicle. Regenerative braking may also be used to recharge the batteries when possible, but overall these vehicles will not have the option for external charging and will rely on gas to charge the batteries. Plug-in hybrid electric vehicles have a larger battery than the standard hybrid, giving them a longer range of around 10 to 40 miles on pure battery power. This means that common drives such as your daily commute may be made on only battery power. Longer drives, though, will require the use of the internal gas engine, but unlike a pure electric vehicle, the plug-in hybrid won't be restricted due to lack of charging station availability, making some consumers more comfortable with this option over the fully electric vehicle. This is one of the reasons that plug-ins are expected to make up a significant portion of EV sales in the next decade. The pure battery electric vehicle has no internal gas engine or generator. It relies only on battery power 100% of the time and requires an external power source to charge its batteries. The batteries in the fully electric vehicle are much larger than the standard hybrids and PEVs, and thus the range is much greater, between about 100 and 400 miles, allowing it to accomplish a lot more on a single charge and putting it close to the range of a standard gas-powered vehicle. And unlike the plug-in hybrids, the battery electric vehicle is a true zero-emission vehicle. Now we'll take a look at the different charger types and levels and where they may be applied. Regardless of power level or charger type, the general parts of an EV charger are the same. Power must be transferred from the grid to the vehicle, and since the batteries require DC power to charge, AC to DC rectification is needed. The AC source could be single or polyphase and may be more or less susceptible to electromagnetic events depending on the charger location and may require EMI filtering and surge protection. The charger must also stay within the harmonic current limits to maintain power quality, which means power factor correction will be needed. The AC to DC stage usually combines rectification and power factor correction functions using a single high frequency switching converter. At low power levels, this could be as simple as a boost converter, and at higher power levels, more novel topologies such as the bridgeless totem pole may be used to reduce losses associated with the rectification. The output of the AC to DC stage is a high voltage DC that is often fed into a DC to DC stage. For safety and efficient charging, battery charging follows a specific voltage and current profile. During certain portions of the charging cycle, the battery may require constant current or constant voltage. The DC to DC stage takes the high voltage from the AC to DC stage and converts it to the battery voltage according to the charge profile. And last, there's a battery management unit that controls the process and whose purpose is to protect, monitor, and balance the battery cells. It monitors the state of health and the state of charge of the battery cells and balances them to optimize their life and efficiency. The energy transfer from the grid to the vehicle may either be wired or wireless. Wired transfer through conduction is the more common and simpler method. This method uses physical contacts to conduct electricity between charger and vehicle. And with this method, power from the grid side may be delivered to the vehicle either as AC or DC. This type of charger is also usually stationary due to the need for physical contact. For wireless charging, rather than transferring power through a physical connection, wireless chargers use electric or magnetic fields to transfer energy from the grid to the vehicle. And this leads to two wireless charging types, inductive and capacitive. With wireless charging, the vehicle is DC isolated from the roadside power source, and so only AC power may be transferred. Wireless charging also offers several advantages over conductive charging. The primary one is convenience, not needing to physically plug your car in every time you get home from work, but instead just drive onto a charging mat in your garage or park in a wireless charging space in the parking lot can make charging a lot less tedious. And these type of chargers don't necessarily require a stationary vehicle, as there's no cable tethering it in one place. This can also increase reliability as the cables tend to wear out over time as there's physical contact between the vehicle and the cable. Ideas are out there for wireless chargers to be built into or above the road itself to charge vehicles as they're driving, potentially eliminating any need to stop altogether. Some companies, such as Tesla, have said they see this as a key part of the future of autonomous driving. The inductive power transfer method is relatively simple. The grid voltage is rectified to DC, and then an inverter converts it back to a high frequency AC. This is applied to a coil on the transmitting side of the charger, which creates a magnetic field that couples with a receiving coil on the vehicle side, just like a transformer. From there, the voltage is converted back to DC and regulated for the battery. Some wireless charging methods simply substitute a conductive charging plug with a magnetic paddle. This doesn't provide the convenience of charging pads or in-road charging coils, but has the benefit of less mechanical stress, potentially increasing the reliability. For the charging pads and in-road coils, the relatively large distance between the primary and secondary coils means that there's poor magnetic coupling, which can lead to low efficiency. This method also requires ferrites to direct the magnetic field, which makes them heavy, expensive, and relatively fragile. The components on the vehicle side must also be kept small and light so they don't further encumber the vehicle and reduce the range. This means operating at high frequencies. However, core losses are an issue that can limit the frequency and potential size reduction. High frequency magnetic materials are needed to limit these losses, but also add to cost. Semiconductor losses are another concern. New wide band gap semiconductor materials and processes have helped here by reducing switching losses and pushing switching frequencies to new levels. This has enabled a wide range of converter topologies that were previously limited by their switching losses. Silicon carbide and gallium nitride devices are already being used in some chargers, and the reduced losses offered by these devices can lead to smaller and more efficient chargers. CUI has been using gallium nitride devices in some of our power supplies for the very same reason, and we've seen form factors reduced by as much as 50% compared to the conventional silicon designs. And because wide bandgap devices are still relatively new, they still have plenty of room to grow and improve over time. Compared to the conductive methods, though, the inductive method is relatively expensive and difficult to install in the roadway, and the vehicles must be equipped or adapted with the necessary coil and conversion equipment, which can be expensive on the vehicle side. While it may not be widely available now, many see this as a critical technology of the future, fast charging infrastructure, and with enough wireless chargers built into the roads, it's thought that the size of the EV's battery could be reduced, leading to reduced weight and increased efficiency of the EV. Capacitive energy transfer uses electric fields rather than magnetic fields and parallel plates rather than coils to transfer power. Compared to the inductive power transfer, there is no ferrite, which reduces the weight and doesn't limit higher frequency operation. Where the inductive method may operate in the tens to hundreds of kilohertz range, capacitive charging can operate into the megahertz range. Compared to inductive charging, capacitive is less expensive and easier to install. The newer wide bandgap semiconductors, gallium nitride and silicon carbide, can help here as well, enabling an increase in the switching frequency while limiting losses. One downside to this method, however, is relatively high electromagnetic emissions, which must be controlled so they don't interfere with other equipment. Conductive charging is the most common method and looks to remain so for some time. These chargers are widespread and highly efficient, but don't offer the convenience of wireless chargers as they must be manually plugged in to charge and are also stationary. But they require little maintenance and have low electromagnetic emissions compared to wireless methods. These chargers connect to the vehicle through a cable that makes contact through a plug over, with, over which both charging and communication takes place. One downside, though, is that the physical nature of this method can lead plugs and cables to wear out over time, whereas wireless methods have no cable or plug to wear out. But the simplicity of this method makes it more cost effective and doesn't require any special vehicle side receiving equipment other than the connector itself. In addition to being wired or wireless, chargers may also be uni or bidirectional. This enables both vehicle to grid and vehicle to vehicle charging. Vehicle to grid charging enables vehicles to provide power back to the grid. One scenario in which this may be useful includes delivering power to the grid during peak demand times and recharging during low demand times to both reduce your power bill and ease the stress on the grid. The EVs can essentially act as grid energy storage devices with their onboard batteries. They could also serve as auxiliary power during a blackout or help reduce stress on the grid by supplying power during transients. The problem with bidirectional power flow include increased battery degradation caused by the frequent charging and discharging, and these chargers also tend to be much more expensive. Consumers also could have concerns about the unpredictability of the state of charge. When they need to drive, they want the batteries to be charged, but if the vehicle has been sharing its power with the grid or another vehicle, unbeknownst to the driver, they might not have as much charge as they expected when they get into their car. The power delivered to the vehicle from the charging station may also be AC or DC, even though it ultimately ends up as DC for the battery. For AC chargers that deliver the grid voltage straight to the car, AC to DC rectification, DC to DC conversion, and battery management all take place in the vehicle in a so-called onboard charger. Because all the charging equipment is on the vehicle, the charger needs to be made as small, light, and cost-effective as possible so that it doesn't reduce the range or inhibit consumers from purchasing. But it also must support the desired charging speeds. DC chargers perform the rectification and conversion external to the vehicle and deliver the battery voltage directly to the battery management system. In this case, because the power electronics are primarily off-board, they aren't as restricted in size, weight, and cost as the onboard charger is. Between AC and DC charging, the placement of the charger either on or off-board is the main difference. Including the battery charger in the vehicle can add some considerable weight. However, it gives access to a wide range of charging options. Removing the onboard charger and relying only on DC charging isn't very practical, at least at the current time, due to the lack of DC chargers and the fact that they aren't for home use. Because the charger is not in the vehicle in this case, it's also not as critical for it to be small and lightweight, therefore allowing for much higher power levels than an onboard charger. Many electric vehicles are designed with combo plugs such that either AC or DC may be supplied to the vehicle. In the case of DC, the onboard charger will be bypassed and the DC voltage will charge the battery directly. Wireless chargers also require an onboard charger as they deliver high-frequency AC power to the onboard charger, which must be rectified and converted the same as if it were plugged in. Safety standards have been created that classify EV charging stations by power level and type. One of the first standards came from the NEC in 1999, and in this standard, charging stations were divided into 3 levels, all of which were for AC charging. Level 1 defined slow AC charging and used a standard convenience outlet to provide power from the grid. Level 2 was a little bit faster charging and worked off 208 or 240 volt AC and had power levels up to 7.68 kilowatts. Level 3 was the AC fast charging level, which operated off of 3-phase 480 volt power and was much faster but also required a much larger and more expensive service equipment. The SAE International later defined their own set of levels in their J1772 standard. This standard applies to North America and defines 4 levels. In this standard, DC charging is added and split into 2 separate levels, giving a total of 2 DC and 2 AC charging levels. Internationally, the IEC in their 61851-1 definition defines modes instead of levels, and similar to the SAE standard, it has 4 modes, which include 1 DC mode. The variety of standards can make things a little bit confusing, and perhaps because of that or because it was one of the first classifications of chargers, the original 3-level system seems to have stuck, even though other standards have come about with a different number of levels. It's still common to see chargers divided into 3 categories. However, these are usually 2 AC categories and a DC fast charge category. So we'll take a closer look at each one of these 3 charger levels. Level 1, sometimes called AC slow charging, is the lowest and slowest power level. With this level, the EV plugs into a standard 3-prong outlet, just like you'd plug in any home appliance. For the IEC, this is similar to their Mode 1, but the IEC specifies either a single-phase voltage limit of 250 volts or a 3-phase limit of 480 volts. The power is limited by the current rating of the outlet, which is 16 amps in the North American case, and makes it the slowest charging level. For the NEC and SAE, level 1 has a max rating of 1.9 kilowatts, while the IEC limit is 4 or 11 kilowatts, depending on whether the source is single or 3-phase. The main benefits of this charger are the fact that there's no costly installation required. All that's needed is the charging cable, which usually contains a small box between the EV and the convenience outlet. This box and cable contain minimum electronics for interlocking and protection, and the cable costs between $1 and $500. These converters, due to the low power, also don't stress the grid very much compared to other chargers. This type of charger will primarily be found in homes and be used for charging overnight where speed is much less critical than cost. Level 1 chargers contain the bare minimum circuitry. The AC input feeds into a contactor, which makes or breaks the connection with the EV. The contactor is controlled by an MCU, which monitors the EV charge status via the control and proximity pilot signals. And simple LED indicators are used to relay charge status to the user. The power requirements for the level 1 charger tend to be very low due to the simplicity. A low power isolated AC to DC power supply is needed to generate the main DC bus, which is typically around 12 volts. This power supply needs to be compact as everything needs to fit into a small box, usually connected to the cable. Because these chargers will be found in the home, the electromagnetic emission should fall within Class B. And in order to fit in the small form factors required by Level 1, it often makes sense to apply the EMI filtering external to the power supply, instead of choosing a power supply with built-in filtering. Doing this provides more flexibility to the designer. There's no guarantee that the built-in filter will pass your end system's filtering requirements, and it may make the power supply larger than you can allow. An externally applied filter can be tuned to your system needs, but also gives you more freedom in placement and can allow for much more compact designs. A high efficiency is also needed to limit the need for thermal management. Level 1 chargers will typically be powered from a single-phase residential outlet, so a standard universal input voltage range will work for both 120 volt and 240 volt chargers. Although three-phase chargers define an IEC standard that run on 480 volts will need a wider input voltage range to work. It's also good to have some resistance to moisture and contamination, either by encapsulation or conformal coating, as these will potentially be in an outdoor environment or in a place like a dusty garage. And of course, they must be low cost so that the equipment is a reasonable price for consumers. The 12-volt rail won't be heavily loaded with just the relays and LEDs, and it could be as low as a few watts depending on the design. Non-isolated DC to DC regulators are also needed to generate the MCU's power rail. 5 volts in this case, but it could be 3.3 or lower. And one is needed also to create the negative 12 volt rail for the control pilot, which requires a plus and minus 12 volts. A separate dual output DC to DC could be used for this, but for cost savings, the positive 12 volt rail often comes from the AC to DC. Like the AC to DC, these converters should be efficient, low cost, and have a small form factor. An LDO or switching regulator may be used for the 5 volt MCU rail, but a switching regulator is used to generate the negative 12 volt rail. Level 2 chargers are also AC chargers, sometimes referred to as AC quick chargers. The NEC specified level 2 chargers up to 7.6 kilowatts, but SAE increased this level to 19.2 kilowatts, which is 10 times greater than level 1. Under the IEC's modes, Mode 2 is similar to NEC for single phase, with a 7.4 kilowatt limit, and similar to SAE when 3 phases are used, with a limit of 22 kilowatts. For level 2 chargers, rather than use a standard outlet connected to the grid, level 2 chargers use a 240 volt outlet or a dedicated hardwired installation. These chargers operate off 208 volts or 240 volts AC, and their increased power rating can bring charge times down to 2 to 6 hours, depending on the battery size, and much less than that for a plug-in vehicle, as low as an hour to fully charge a PHEV. With this charge time, an EV or PEV could easily be fully charged overnight or while at work. Even short stops at places like the supermarket could significantly charge the battery over an hour. Plug-ins with their smaller batteries can benefit a lot from this charger, as they need to be recharged more frequently. Like the Level 1, because these are AC chargers, an onboard charger is required to rectify and convert the input voltage. These chargers are more complex than Level 1 chargers. They're a bit larger and a bit more expensive, but still affordable for private use. They contain extra safety precautions such as monitoring and protection circuitry, and they also have displays to interact with the user. But other than that, they're very similar to Level 1 chargers, just a little bit higher power level. The combination of speed, simplicity, and cost effectiveness makes the Level 2 charger the dominant charger type. These chargers are useful for both public and private charging, whereas the Level 1 charger is mostly isolated to home use. Inside the Level 2 charger is much the same as the Level 1. The main difference is more sophisticated display and extra monitoring and protection circuitry. Again, the main rail is generated by an AC to DC power supply, usually at 12 volts. Level 2 chargers are still cost sensitive as they are meant for home use and still should be kept small as possible. A major difference is that rather than being fed from a convenience outlet, level 2 chargers are usually hardwired installations, which means they fall within the overvoltage category 3 and require more protection against surges. Power supplies specifically designed and tested for this environment should be selected. Unlike level 1, level 2 chargers will be found outside the home as well. Parking lots at grocery stores and other businesses may contain these chargers. And unlike the home, chargers in parking lots will have much less protection against the environment. This makes a wide temperature range a must, as well as extra protection from dust and debris. This can be accomplished with an encapsulated power supply or with the use of conformally coated PCBs. Many industrial power supplies can be made like this to reduce the risk of contaminants that can cause failure. The other rails may be generated in the same way as level 1, but like the AC to DC, should have wide operating temperature ranges and high reliability. Level 3 is for DC charging and sometimes called DC fast charging. These chargers apply a high voltage of up to 1000 volts DC directly to the battery management system. SAE divides DC charging into two levels with 80 and 400 kilowatt limits, while IEC defines mode 4 as fast DC charging but only allows for up to 400 volts and an 80 kilowatt limit. DC fast chargers can reduce the charge time to under an hour and pushes them much closer to the refueling time of a gas-powered vehicle. Because of this, an onboard charger is not strictly needed, the removal of which could reduce the weight and increase the drive distance of an EV. However, as we've already mentioned, removing the charger from the vehicle is impractical, as until DC chargers are widespread, you could be left without a charging option if you're only dependent on DC. For the time being at least, vehicles will continue to have onboard chargers, and in these cases the DC charger will bypass the onboard charger. These chargers tend to be much more complex as they contain an off-board charger, more protection, circuitry, and full displays. With this complexity comes size, cost, and power. DC chargers are much larger, much more expensive than the AC chargers, and because of this, it doesn't make a lot of sense for home use and will be restricted to public charging locations, not inside the home. And this will make them the least common type of charger to be seen. This charger type will be more useful along highways so that EVs may quickly recharge on long trips. Typical in-town driving will mostly be handled by level 2 chargers. Inside the level 3 is much more than in the AC charger case. In addition to the contactor, MCU, and measurement circuits, there's potentially an interactive LCD display, security monitoring, as these will be placed in public locations, metering and payment systems, additional communication protocols, etc. In many ways, it could resemble the pump at a gas station. Since the charger is an off-board charger in this case, the battery management system will have to communicate with the charger across the charging cable, typically via CAN bus. To support the additional functionality of a large power supply, To support the additional functionality, a larger power supply will be needed than that of the level 1 and level 2 chargers. These chargers could require 100 watts or more from the AC to DC. The voltage may also be increased to 24 volts, and a second power supply may also be required to power the BMS. The power supply in this case must have a wide input range so that it can operate off of three-phase line voltages up to 480 volts. A standard universal input power supply can only accept an input to about 264 volts. To operate off of a three-phase 480 volt input, the power supply must be designed such that it can accept a nominal 277 volts with some margin. Wide input power supplies can usually be found that are rated for 305 volts for 480 volt applications. Level 3 equipment also tends to be much larger than others. It's higher power and has more features, but also doesn't need to fit in your home garage, so the power supply isn't as tightly constrained size-wise. DIN rails and metal enclosed industrial power supplies are common choice for the 12 volt and 24 volt rails. Like the level 2 chargers, these will also have to be able to withstand a wide temperature range. A charger in Portland, Oregon, where CUI is located, could have seen ambient temperatures over 47°C and as low as -4°C in just the last 6 months. Wide temperature variations can cause a lot of problems for power supplies if not designed for it. At low temperatures, the bulk capacitors in a power supply are much less effective as their capacitance will drop significantly. This can cause power supplies to have trouble starting up, regulating, and can have much larger ripple than under warmer conditions. At high temperatures, the power supply could overheat and either go into protection mode or fail. Both cases could cause the charging station to not work, which is obviously not acceptable. These chargers are also fixed installations with high surge potential and therefore must have increased immunity suitable for an overvoltage Category 3 application. Non-isolated regulators can be used for the secondary rails, such as the rail for the MCU. With the variety and varying power levels have also come a variety of charging plugs. These plugs may be designed to support one or more charging levels. The Combined Charging System, or CCS, is one that is found in the US and Europe. Companies such as Ford, GM, VAG, and BMW use it. CCS specifies two combo connectors, the Combo 1 and the Combo 2. Shown in cell 1 here is Combo 1. The circular upper half contains connections for single-phase AC charging, in addition to line, neutral, control pilot, and proximity pilot. The lower half of the plug contains plus and minus contacts for DC charging. The Combo 2 connector, shown in the third cell, is meant for more powerful, faster charging. It has connections for a three-phase input on the top half, plus control pilot and proximity pilot, and it has DC connections on the bottom half for DC fast charging. Charge to Move, abbreviated as shown in the second cell, began in Japan in 2010 and is followed by many Japanese automakers. It's based around IEC 6185 and 62196. The two large circular contacts are for DC charging, while 8 contacts, 4 each around the X's, contain AC. In addition to standardized connectors, there are also proprietary connectors, such as that of the Tesla, shown last. Tesla has multiple plug types and support different power types and levels, supporting up to 250 kilowatts. As more and more EVs end up on the road, there will be more that are charging at any one time. As with everything, there will be peak demand times and low demand times. This can cause large imbalances that reduce the quality of the grid power, reducing the life of or even overloading transformers, and has led to the development of coordinated charging strategies. Uncoordinated charging is when the charger starts charging immediately when plugged in, or potentially after a defined delay, and doesn't consider what else is connected to the grid or any other conditions. This can cause problems if everybody decides to charge their car when they get home from work. It can lead to voltage surges and sags, increased power losses, and reduced reliability of an already aging grid. And studies have shown that as EV adoption increases, uncoordinated charging will cause a significant increase in peak load demand. Utility companies offer cheaper rates at certain times, such as nights when demand is low, in order to try and shift demand to those periods and balance it out over time. Coordinated charging considers time, power levels, grid, and vehicle conditions, and attempts to charge the battery at a time and rate that minimizes the impact on the grid and is more cost effective for everybody. Because of the high power levels, applying coordinated charging strategies to level 2 and 3 equipment will have the biggest impact. There are still concerns, however, about how consumers will feel about this. They will want to be sure that their vehicle's charge is predictable and that they won't be surprised by a low battery caused by coordinated charging schemes. It would be pretty frustrating to have to charge to have your car plugged in all night only to find out that your battery didn't charge because your charger was trying to coordinate with the grid. To summarize, EV adoption looks to increase significantly over the next several decades as technology advances and climate change concerns grow. To help facilitate the transition from gas-powered to electric vehicles, a variety of charging levels have been created to accommodate the many different driving scenarios faced by the large variety of drivers. Each charger type is meant for different locations and different use cases, and by placing them strategically, an EV driver will be confident in their ability to maintain the charge of their vehicle without the need for long inter-trip stops. Improvements to the power electronics in terms of size, weight, and efficiency can also improve range. New wide bandgap devices are helping to push efficiencies and switching frequencies to new limits, enabling the shrinking of size and weight of the power electronics. Wireless charging methods are being developed that can help increase range and reduce range anxiety by integrating chargers into the roads themselves to facilitate mobile charging so that EVs never have to stop. You can imagine one day when self-driving cars are the norm, your food supply and cabin fever would essentially be the only things that could force you off the road. However, to support a new fleet of EVs, infrastructure concerns will also need to be addressed. To avoid quality and stability issues with the grid, coordinated and bidirectional charging are methods that can help maximize the efficiency of the infrastructure as the number of EVs continue to grow. And that's all I have for you today. I hope you enjoyed the presentation, and now we'll get ready to answer some questions.